On here with number 5. The plot below shows the position of an object. So again, we have position here. The letters H through L. At which moment in time is the speed equal to 0? All right, so again, remember here that velocity equals the slope. All right, if we want 0 velocity, that's going to be a 0 slope. So 0 slope is when it's flat. So right at the top here, that's where it gets to a flat spot. So that would be I. At least those are a little faster. All right, number 6, the motion of a car and truck along a straight road are represented by the velocity time graphs below. The two vehicles are initially alongside each other at t equals 0. All right, so they're starting at the same position, and then the truck is moving with a constant velocity. All right. At time t, all right, what is true of the distances traveled by the vehicles? All right. Well, this one starts with initial velocity vi. The car here starts with initial velocity vi equals 0. So the car starts out going slower, and then eventually at time t they've reached the same speed. But that means car has been going slower the whole time than the truck. So if it's gone slower, it can't have gone the same distance. So we'll have to say here the truck will have traveled farther than the car. Another way to look at this is you remember the area under a velocity graph is equal to the total displacement. So we can see here that the car's area is the triangle, whereas the truck's area is the whole rectangle. So actually the car has 1/2 the distance traveled. All right. Let's go to number 7. Two identical objects, A and B, fall from rest. Okay, rest, VI equals 0, from different heights to the ground. All right, so these things are going to start falling down. If object B takes twice as long as A to reach the ground, what is the ratio of the heights A and B fell? All right, so there we need to think about an equation. And we got an equation for something falling here. We know that delta x is equal to 1/2 a delta t squared when VI equals 0. All right, if it doesn't equal 0, then we have the VI delta t in there. But since it's from rest, that's all going to go away. And we have this equation here. So if we're thinking about that the time is doubled, what's going to happen to x? All right, well, the square matters. So if you make delta t twice as big and you square it, delta x is going to be 4 times as big. So that gives us this letter here. I got children. So let's see, we're going to number 8. A ball is thrown vertically upward and then comes back down. During the ball's flight up and down, its velocity and acceleration vectors are. All right, so let's just draw a picture of that. A ball is going to be going straight up. It'll start slowing down, and eventually it stops, and then it's going to start coming down. All right, so I'll just draw these little dots here. All right, I drew the velocity vectors because it shows that the speed's going up and getting less and less, and then the velocity is down and becoming larger and larger velocity, but in the down direction. So the velocity arrows are changing direction. But now if we think about the acceleration, the only force on these objects is gravity. So the acceleration is only going to be down. Acceleration of gravity, the direction of gravity does not change. So they're not always in opposite directions. They're not always in the same directions. At first, they are. So we got up versus down. So they're going to be in opposite directions. And then, yeah, they're going in the same direction. So I'll take C. All right, number 9. A racing car accelerates uniformly from rest along a straight track. This track has markers spaced at equal distances. The car reaches a speed of 140 kilometers an hour as it passes marker 2. All right. Whereabouts on the track was the car when it's traveling half this speed, 70 kilometers an hour? All right. Well, if it has a uniform acceleration, that's another word for constant acceleration. So that means that if it takes however long time to get to 140, at 70, it's going to be half the time. So I'll put half the time. So, sorry about that. Now the question is, if we're at the full distance at 140, where will we be at half the time? Well, again here, we have this whole delta x is equal to 1/2 a delta t squared. But now we have this question is, if at the full time we get the full distance, where will we be at half the time? Well, if you have half the time squared, that's going to give you 1/4 the distance. So you're actually going to be back here at half the time. Another way to look at that would be to think about this graph here. If we have a velocity time graph, velocity versus time, and at marker 2, at marker 2, we're getting, so this is our area. This full area would be marker 2. At half the time, we have a much smaller area than half of the total area of that triangle. So since you have less than half the area, you're going to be before marker 1. And that's the answer here. So a couple different ways. You can do it with the equation. You can do it visually with the graph, that the area under velocity graph is your displacement. So there's some different ways, different tricks to looking at those. Let's see, how many more questions do we have? Oh, 4 more. Better take another pause.